Broadcast too, is that?
Live to Google Video.
So this is Mike Hansen. He is visiting us for a couple of days in case, I guess I hope you, well, he'll be around this afternoon.
Yeah.
If you want to talk. And he's going to talk about stage and symmetric functions.
Okay, thank you. So as Professor Billey mentioned, I'll be talking about Sage in the first bit of my talk. And then some of the stuff I've been doing recently with Sage involves symmetric functions. So I'll give a bit of an introduction to symmetric functions and then show you sort of how they work in Sage and sort of give you a feel for how one may use Sage to work with these sorts of things. So a good place to start, well, here's sort of what I'm going to be talking about. But a good place to start would be, what is the goal of Sage? So the goal of Sage is to create a free, viable alternative to Maple, Mathematica, MATLAB, and Magma. These are sort of like the four big M's that kind of dominate, say, computer algebra systems. They've been around a long time and are sort of like pervasive throughout the math community. What is Sage? Now, Sage is a distribution of open source math software. So one of the things Sage does is collects a good number of the open source math programs that have been written. There have been a lot of them, but they're in many cases small, pretty specialized tools that are designed for one particular purpose. So it's a distribution of free open source math software. If you go to the website sagemath.org, you can find a 150 megabyte file which contains the source code for all of these programs. And it's pretty easy to build, and it takes maybe about an hour or so on a modern computer, and will give you Sage. So in addition to collecting all of these sort of already written open source math programs, Sage provides a whole lot of new readable code written in the Python programming language, which I'll mention a bit more about later on. And the goal of this code is sort of twofold. One is to integrate all of these sort of disparate open source math programs together, and then also to implement new algorithms and sort of functionality that's missing in the sort of current open source math world. And one of the features of Sage that I find particularly neat is it provides a unified interface to much of like the existing mathematical software. For example, Magma, Macaulay 2, Singular, Maple, MATLAB, Mathematica, Axiom, and many others. If you can think of a sort of math software that you could use from like a command line interface, there's a good chance that Sage has an interface for that. So if you have, say, Maple or Mathematica installed on your computer and you're running Sage, then you can use that as sort of like an engine in the background to do the computations, spit them back to Sage, and then manipulate them within Sage. So why use Sage? This is a quote that comes up a lot when talking about Sage. So it starts off as, you can read Seelo's theorem and its proof in Hubert's book in the library, and then you can use Seelo's theorem for the rest of your life, free of charge. But for many computer algebra systems, license fees have to be paid regularly, and they're just sort of black boxes. You press buttons and you get answers in the same way that bright pictures from your television. You get bright pictures from your television set, but you cannot control how they were made in either case. So with this situation, two of the most basic rules of conduct in mathematics are violated. In mathematics, information is passed on free of charge, and everything is laid out in the open for checking. Not applying these rules to computer algebra systems that are made for mathematical research means moving in a most undesirable direction. Most important, can we expect anyone to believe a result from a program that he or she is not allowed to see? Moreover, do we really want to charge our colleagues in Moldova several years of their salary for a computer algebra system? And this quote is from J. Noy, Buser. My German is not very good. And he was the one who started the GAP system in 1986, which is probably, well, by far the best computer algebra system for working with group theory that is open source. So here's sort of the how Sage came to be. In February 2005, it was started by William Stein, who's here in the audience, and he released Sage 0.1, a Python math library. So if you look at the dates, like February 2005 is not so long ago, and especially when you think about it in terms of sort of the computer algebra world. Both Maple and Mathematica were started in 1988, which puts them at nearly 20 years old. MATLAB was started in, I believe, 1984, and Magma, I believe, was from the early 90s. So those programs have been around a long time, and they've had that many years for people to develop them, and they also have like the resources, like much more money than, say, Sage does. So in February 2006, 1 year later, the first Sage Days was held, and Sage Days it's a chance for like developers to get together, work on Sage, come up with, brainstorm new ideas for it, and give talks, and just sort of, do Sage development. So the first one was held at UCSD in February 2006. In October of that year, one was held here at the University of Washington. In March 2007, Sage Days 3 was held at UCLA at the Institute of Pure and Applied Mathematics. And that's actually where I first heard about Sage and got involved with it. I had been using some Python before for my own math research, and then when Sage came about, it was like only natural for me to start doing stuff in Sage since I was doing in Python already. June 2007, so just this June, there was a Sage Days here at the University of Washington. A month ago, well, earlier this month, I guess, there was a Sage Days at the Clay Math Institute, and with focus on arithmetic geometry. Yeah. And here in 2 weeks, there's going to be Sage Days at the Hildron Institute in Bristol, England. So these Sage Days, well, they're becoming more and more frequent, which is a good thing. We are able to get some funding and start bringing together groups of people to all sort of work toward one common goal of a sort of free open source math software. So right now, Sage is at version 2.8.10, and there are probably around 100 contributors to Sage. So in the future, it looks like Sage Day 7 is going to tentatively be on Combinatorics sometime around February. So there's starting to be a bit more interest in using Sage for combinatorial type problems.
If there is Sage Day 7, it will definitely be on Combinatorics.
Okay.
So, but IPAM decided between Combinatorics and numerical computation, they wanted Combinatorics. So.
Yeah, so pending approval of that,
yeah.
There will be Sage Day 7 on Combinatorics. So I think one of the nicest things about Sage is that it uses the Python programming language to use it or to write new algorithms in it. And so Python is a modern interpreted programming language. And so here are two different quotes, one from a software architect from Google, and one from Guido Ben-Rossum, who's at Google, and he's the creator of Python. So it's fast enough for YouTube to produce maintainable features in record time with a minimum amount of developers. And Guido Ben-Rossum says that Google has made no secret in the fact they use Python for a number of internal projects. Even knowing that once I was an employee, I was amazed at how much Python code there was actually in the Google source code system. So Mathematica, Maple, all of those, they have sort of invented their own programming language, and that's what you use to to write programs in Maple. And Sage is the first time a standard programming language has been used within to use a computer algebra system. And I think that there's a number of reasons why this is like a very, very beneficial thing. So it's easy to define your own data types and methods in Python. And so if you're used to working with, say, Maple, there's no real notion of a data type. Everything is just sort of an expression. And so being able to have typed data makes it much easier to do math on computers. It's a very clean language, and the code is very easy to read. If any of you have looked at math software, it can definitely be a challenge to figure out what someone is doing, especially if you aren't, intimately familiar with the code. So it's easy to learn. There are free Python tutorials at those websites, and there are a huge number of libraries, not necessarily pertaining to math, that you can use within Python. So there's libraries for doing statistics, networking, databases, bioinformatics, and so on. And so using Python makes it easy to incorporate all of these into Sage. It has excellent support for string manipulation and working with bits. And it has Cython, which is a Python compiler. It allows you to easily intermix Python and C. So you can write code that's pretty much a superset of Python and then compile it to C. So this allows you to write things that are very fast, which is necessary for doing arithmetic and all sorts of basic operations. But it also allows you to interface with all sorts of existing C software and libraries. Okay, so if you download Sage on your computer and open up command prompt and type in Sage, this is what you get. The current version is 2.8.10, and you get a little prompt here. You can do 2 plus 2, and thank goodness Sage gives us 4. And if you run the command notebook, it'll open up your web browser to the Sage notebook. And so for its graphical user interface, Sage actually has a web interface. So you use just like a normal web browser to use Sage. This has some nice advantages in that you could say run your Sage server on a big powerful server in the department, and then just access it via a web browser on your local computer. You can create embedded graphics in the notebook, typeset mathematical expressions. There's actually an implementation of the tech layout engine, so you can get nice typeset graphics in your web browser. You can start and interrupt multiple calculations, and you can also change the mode of the notebook. You could say switch the notebook to Maple mode, and then you can use Maple from the notebook interface, and that totally bypasses Sage. So if you're really used to working with Maple, or you want to create some worksheets in Maple, then you can use the Sage notebook and have those sort of side by sides with your Sage worksheets. So here's some of the packages and functionality that Sage includes. So there's over 200,000 lines of new code in Sage in Python that, as I said before, ties together many of these existing libraries and also provides a whole lot of new functionality. There are definitely things in Sage that you can't do in any other computer algebra system. So for algebra and calculus, the standard, what used to be the standard open source computer algebra system for doing symbolic calculus is Maxima. And there's a relatively new project called SymPy, which is a pure Python implementation for working with integrals, limits, all those sorts of things. You have arbitrary precision arithmetic, so GMP, is by far, I think, the fastest library for doing integer arithmetic. MPFR for doing arbitrary precision real arithmetic, and NTL, the number theory library, has some code for doing arbitrary precision arithmetic as well. Sage includes Singular and Macaulay 2. Macaulay 2 is an optional package which provides a lot of functionality for algebraic geometry. Exact linear algebra, group theory, Sage includes GAP, and so anything GAP can do, you can get its functionality through Sage. And then also there's some numerical stuff. You can use GSL, which is the GNU Scientific Library, SciPy and NumPy, which are sort of the Python equivalents for doing numerical computations. They provide a lot of the functionality that you would find in, say, MATLAB. So, with all of these and the sort of 200 lines of new Python code, you can probably do whatever math you want to do using Sage, or even if you can't, it would be easy, relatively easy to implement it in Sage.
Well, there's more than this, right?
What?
There's more than this.
Yeah, there's more than this. But these are some of the bigger packages. Yeah, so as I mentioned before, these interfaces allow you to, like if you find a piece of software written using one of these computer algebra systems, you can make use of it from within Sage by using the interfaces, which I will demonstrate here shortly.
Yeah.
Go ahead.
So like John Stem, which is a symmetric functions package, do you guys have that in there? Even though you might not have Maple in the distribution?
No, so...
Like free Maple packages could be included.
Yeah, I don't know how exactly that would go, but if you have Maple on your computer and you have John Stembridge's package, then you can do that. So I'll give a little demo of some of these things with using Sage to do some of these things. So here's the notebook. This is a web browser, and I started a new worksheet. So I'm going to hide the bar. And so if I do 2 plus 2, we get 4. You can also do things like, say, plot sine of x between -5 and 5. And then show it in the browser. So it will generate the graphic. And there it is. If you save that plot to... Can everyone read that okay? Should I make it bigger?
Fine.
Okay. If I assign that plot to an object P, then I can save it to many different formats. One of the nice things about the notebook is if you put a question mark after any object, you can get sort of a little help file for that. So here, this save command, you can save it to PNG, PS, EPS for like inclusion in like a LaTeX file, scalable vector graphic, or a Sage object that you could move around and say send it to someone else and they could load it up in their copy of Sage. So you can do all of your familiar commands like integrate x squared in terms of x. There you get that. Say solve 2 times x equals 4 for x. Yeah, x equals 2. And so for those things, what it's really doing is it is using maxima in the background. So this functionality is not included in Sage itself. But Sage knows how to turn in what you type there to an expression that maxima can understand. And then it can send it back to Sage, and you can work with it as sort of native Sage objects. Okay, so that's sort of your standard calculus functionality. You can work with matrices. So you can define a new matrix. Say 1, 2, 3, 4. And there's the matrix. You can ask what its parent is. So it lives in the full matrix space of 2 by 2 dense matrices over the integers. So if I ask what type it is, so it's a matrix integer dense. So this object has some type, so that the system can realize, oh, this is a matrix over the integers, and you can have like specialized algorithms based on the types. You can do arithmetic with matrices. They don't display very well, but you can see how quickly they computed m to the 100th. So you can create polynomial rings. So polynomial ring over the rationals, where I'll let x be the variable. And so now I have x, and I look at x's parent. It lives in the univariate polynomial ring in X over the rational field. So this is an example of like how everything is typed, and you know exactly where things live and what they are. So I guess I'll do some more combinatoric stuff, since this is the Combinatorics Seminar. And I've been pretty heavily involved with the combinatoric side of Sage, well, pretty much ever since Sage Days 3. So I guess we can play a little game. Does anyone have a favorite combinatorial object?
Tableau.
Tableau, okay. So, well, let's do standard Tableau. And we can create an object corresponding to all the standard Tableau of size 3. And let's say, I'll call it S3. So what are the things you want to do with Tableau? Well, how many are there? There's 4. And what are they? Well, that's a bit better. This one is the one with just 1, 2, 3 across the top. Here are the ones of shape 2, 1. And then here are the ones of shape 1, 1, 1. If I let T be the second one in the list, Python starts its indexing at 0. If you let T be the second one in the list, then there it is. And I can ask certain things about it. So if I press tab, it gives a list of operations that apply to that Tableau.
What does your underscore mean? Does that mean?
Oh, it means the previous.
Underscore? Okay.
Yeah.
How would you do it if it wasn't previous?
Yeah, the
Okay.
thing that was previously evaluated. So I could do it like that instead. So the S3.list gives out that list, and then I pick the one corresponding to index 1. Okay, so I could get sort of like a pretty like ASCII representation of that Tableau, or I could ask what's its shape, and if I look at, so I get 2, 1, and I look at, well, what's the type of that shape? Well, it's a partition. So I could
Does that
do,
mean that's the only definition of the function shape in the whole Sage package? Or
No,
does it
so-
somehow tell it that it should be in standard Tableau so it knows certain commands?
yeah, so one of the things that's different about Sage from most of them, for most computer algebra systems, is that they usually have a whole huge list of functions, and then they take in some argument. So because Python is an object-oriented language, what you do is you have objects and then methods associated with those objects. And so T, this Tableau, has certain methods associated with it, and shape is one of them. So if this were to be done in something like Maple or Mathematica, you'd typically do something like that, right?
Or
You have the-
Tableau dot shape, because
Right, Yeah, but one of the nice things about Python is that like all your objects come with the things that apply to
Can
them.
you show the list of objects that go with standard Tableau?
Yeah. So I press tab. So you get bumping. You can ask if it's rectangular, if it's standard. You could do like multiplication of Tableau using sliding.
And shape for some other type of object would mean something
Else, yeah.
And it's T dot, not for Tableau, but because you define T to be
That object,
Okay.
yeah. So I'll say P equals T dot shape. Now P is some partition. There. And you can ask, well, what things can you apply to a partition? Well, you could get, say all the partitions you get by adding, let's see here. Oh, all the partitions you get by taking away a box. So remember, our partition P was 2, 1. And then a natural thing to do is ask, what partitions do you get by taking away a box? And so those are the ones that you get. Or you can, if you're interested in like modular representation theory of the symmetric group, you can get I guess it's not too interesting in that case, like a 2-core or k-core of a partition. So there's all sorts of there's all sorts of these combinatorial objects that we have in Sage now. Some more examples would be, I could give you permutations of 3, and there they are. I could say, let's say I want the permutations of 3 that avoid the pattern 3, 1, 2. I guess I should make it something else to make it a bit more interesting. Right? So this is an object corresponding to the standard permutations of 4, avoiding 3, 1, 2. And so, well, how many are there? There's 14 of them. Could I get a list of them? Yes. And that's what they are. We have other sorts of these combinatorial classes we have in Sage are set partitions. So I can ask for all the set partitions of, say, 1, 2, 3. And that gives all the set partitions, or
Excuse me, do you have tab completion or do you just type fast?
tab completion. Yeah,
Cool.
There's tab completion within the notebook, which is very helpful.
It was extremely hard to implement. Tom Boothby spent a lot of time hacking JavaScript to get that to work.
We thank
He's an undergrad here.
Yeah, it works very well and is incredibly helpful. So maybe you want ordered set partitions. And so then you can get all the ordered set partitions of that. And there's probably at least 30 or 40 different like sets of combinatorial objects that are in Sage that you can work with. And there's a nice standard interface for like listing them, counting them.
So can you use the ones with 3 parts?
Huh? Yeah. So I forget if I have it for ordered, but I know for this, there's only one of them with 3 parts, but you could ask for ones with 2 parts. You could also ask for all the ones, say I want to partition into blocks of size 2 and 2. So you can get those. There's, I think, quite a bit more you can do. You can generate like all the compositions of 4. There they are. So there's a whole lot of functionality in Sage now for just working with these combinatorial objects. Okay, so that's sort of the first half of my talk. Does anyone have questions kind of about general things in Sage before I move on to talking about symmetric functions? No? Okay. Okay, so I recently, this June, got interested in symmetric functions, and there was actually a workshop for the computer algebra system Axiom. That was, the theme of it was symmetric functions. And so I was over there and became interested in them, and so wanted to provide functionality for working with symmetric functions in Sage. So for those of you who haven't seen symmetric functions, I'll give a brief introduction to them. And the most natural place to start off describing symmetric functions is to talk about symmetric polynomials. So a polynomial in a multivariate polynomial ring with, say, variables x1 through xn is said to be symmetric if it's invariant under any permutation of these variables. So natural symmetric polynomials to look at would say would be like the following ones. So you could have these are polynomials in x1 through x3 that are symmetric, and if you notice that if you swap any two of the variables, then you get the same thing back. So this first one is a sum of the powers of two of the individual variables. This one you get by taking a sum over all subsets of size 2 of the variables. And this one you get by taking a sum of all the monomials of degree 2 in variables x1 and x2. So symmetric functions are generalizations of these. And so a symmetric function is a symmetric polynomial in infinitely many variables. So that if you switch any of the variables, it's invariant. You get the same thing. And so the symmetric function algebra, which is typically denoted by uppercase lambda, is the algebra with these symmetric functions as its elements. And like multiplication between symmetric functions sort of corresponds to the multiplication you would get by if these were polynomials in infinitely many variables. They should match up. So there are several bases for this algebra. So as a Z module or as a Q module. And all of them are indexed by integer partitions. So you have the empty partition, which corresponds to the identity element on the algebra. And then partitions 2 are the single partition of 1, 2 partitions of 2, and the 3 partitions of size 3. So here's the first basis, known as the power sum symmetric functions. And how you define it is you define P sub r, where r is some positive integer. And what you're going to do is you're just going to sum up all the individual variables raised to the rth power. Okay. But as I said before, that the basis elements for this algebra are indexed by integer partitions. So how do we get the element corresponding to an integer partition lambda? Well, we just take all the parts of the integer partition and multiply all of the p sub lambda i's together. And so that's how we'll get a power sum symmetric function. So if I wanted to work with symmetric functions in the power sum basis in Sage, the command I would run would be P is equal to SFA power and then Q cubed. I'm going to look at symmetric functions over the rationals. And so what this does is this creates an object P in Sage that corresponds to the symmetric function algebra in the power sum basis. Okay, so how do I create elements? How do I create symmetric functions in this basis? Well, what I do is I create an integer partition So this one just corresponds to 2. And I pass it in to P. And so what that does is that creates a symmetric function corresponding to the basis element indexed by that partition. And so one command that this object provides is expand. And you can say if you ignore all the variables higher than, well, greater than or equal to 3, and you look at what terms are left, that's what this is. So here you see it's just x0 squared plus x1 squared plus x2 squared, what you think it would be. So here, I create the object corresponding to the partition 2, 1, and then expand it on 3 variables. And then what I do is I create an object B, which I obtain by first taking this symmetric function, expanding it on 3 variables, and then what I get is a polynomial. And I do the same thing for 1, and expand it on 3 variables, and you get another polynomial. And then you perform this multiplication here between polynomials. So this is all happening in a multivariate polynomial ring within Sage. And you check that, well, A and B are the same, and Sage says true. So, well, Sage is doing the right thing, because that's how they're defined. So the next basis that one would want to work with are the elementary symmetric functions. And so as we saw before, we formed these, well, we defined E sub r to be the sum over all subsets of variables of size r. So if we were to switch any of the variables, we'd still get a subset of variables of size r, so it would appear there, and thus E sub r is symmetric. And like with the power sums, you define E sub lambda, where lambda is an integer partition. You just multiply all the corresponding ones together. So I can create this basis in Sage by saying E equals S of A elementary QQ. And here we're going to expand E of 2 on 3 variables, and you get what you think you should get. The next basis for the symmetric functions are the homogeneous symmetric functions, which you get by adding up all the monomials of degree r. And like before, this is a multiplicative basis, so you get h sub lambda by just multiplying all the corresponding parts together. In Sage, the command is S of A homogeneous, and this is the expansion of h2 on these 3 variables. So the next, so these are the 3 multiplicative bases where h sub lambda is given by this product. But there are also 2 classical bases where the multiplication is not so easy, or it's not defined multiplicatively. So what we're going to do is we're going to define m sub lambda to be the sum over all orbits of x to the lambda, the orbits of this monomial under the action of the of the symmetric group. So I guess this needs a bit more explanation. But say we have the partition lambda equals 2, 1. Then one of the terms that's going to appear is x to the x naught squared times x1 to the 1. So those exponents are where the integer partition comes in. Now we have 3 variables, so we can act on that first monomial. By the symmetric group, we can switch variables around. And if we switch those around, because it's invariant, all those terms also have to appear.
So how are permutations going to act on those monomials, because you have those indexing different?
I mean, if you say x naught is the first variable,
Oh, I see, yeah.
and then
No, I mean, but if in Sage, how does it work? Like if you listed your permutations and then tried to apply it, how do you apply a permutation to a polynomial?
right, so this is So I don't think there's code in there right now for applying a permutation to a multivariate polynomial. This stuff is all happening in a C library called Symmetrica, which one of the things I've worked on is making Symmetrica's functionality available through Sage. Because before it was well, just a C library. So if you wanted to use it, you had to write programs in C, which it's not very flexible for just experimenting around, because you have to write a whole new program, compile it, run it, and then if you want to make changes, you have to repeat the process. But because we're using Python, and Python works well with integrating with other libraries, I can have Symmetrica sort of do all the back-end computations fast in C, and then we convert that to the corresponding Sage objects. So these are the monomial symmetric functions. And then finally, we get the Schur symmetric functions. So we define the Schur symmetric function S sub lambda to be the sum over all t, which are semi-standard tableau of shape lambda. And what are we going to sum? X to the t. And so what do I mean by x to the t? Well, here we have a semi-standard tableau. It's a tableau that's weakly increasing along the rows and strictly increasing along the columns. Then what do? If I want to find out the exponent of x1, I look at how many ones appear in that tableau. And so in this case, there's 2 ones that appear, and only 1 2. So we get x1 squared times x2 to the first. And then this is the only other semi-standard tableau of shape 2 1, and that corresponds to this monomial. So if we create the symmetric function algebra in the Schur basis in Sage, through this command, look at the Schur function corresponding to 2 1, expand in 2 variables. Here you get the 2 terms you see up here. Okay, so these 5 bases are the classical symmetric function bases. There's also a scalar product on between symmetric functions, and it's defined by the following relations for the power sum symmetric functions. So we have the scalar product between a power sum symmetric function p sub lambda and one p sub mu is defined to be c sub lambda, which I'll talk about later, times the Kronecker delta of lambda of mu. So this says that the power sum symmetric functions are orthogonal with respect to this scalar product. And we define c sub lambda to be the size of the centralizer of a permutation of cycle type lambda in the symmetric group. So that's just how this scalar product is defined. So in Sage, here's a bit of sort of functional-ish programming in Sage. What I do is I create the object corresponding to the partitions of 4, and then I run this map command. So it takes each one of the partitions of 4, sends it into this function x, and then applies the method centralizer size. So I have a partition, it has a method called centralizer size associated with it, and it gives the size of the centralizer of a permutation of cycle type lambda in the symmetric group. And so for the partition 4, this z sub lambda is 4, for 3 1 it's 3, and so on. So now I want to talk a bit about dual bases. So if we have some scalar product on the symmetric function algebra, and we let a lambda and b lambda be bases for lambda, then we say that a and b are dual to each other with respect to that scalar product, if and only if a sub lambda, the scalar product of a lambda and b mu, is delta lambda mu. So they have to be orthogonal to each other, and when you take a sub lambda or scalar product with b sub lambda, you should get 1. So with the scalar product I talked about before with the z sub lambda in the previous slide, the following bases are dual with respect to it. So here you can see that the Schur functions are self-dual with respect to that. So if you sort of plug in S lambda up there, you see that the Schur functions form an orthonormal basis for the symmetric functions. The monomial symmetric functions are dual to the homogeneous symmetric functions, and the elementary symmetric functions are dual to these, which we didn't talk about, and they're known as the forgotten symmetric functions, just because everyone seems to forget them. And I don't know, I haven't seen, everyone seems to go over them when going through symmetric functions. So here I create the symmetric function algebra in the monomial basis, and then I ask if it's dual basis. When I don't specify anything there, I just get, with respect to the standard scalar product. I ask if it's the homogeneous basis, and Sage tells me true. So things one would often want to do with symmetric functions are perform change of bases between, say, the Schur and the power sum, or any of them. Perform multiplication. So for all the multiplicative bases, the multiplication is really easy, but it's a bit more involved in, for say, the Schur functions. And there's some nice combinatorics underlying that multiplication. Compute these scalar products, or maybe you want to define your own scalar product and, like, say, specify it by telling what the scalar product between two power sum symmetric functions are. That's a natural way to define a scalar product on symmetric function algebra. And so maybe you want to compute those, or plethisms, where it's like you compose one symmetric function with another, is a typical operation you want to carry out. And you can do all of these in Sage. So I'm going to give, a little bit, give a bit of a demo of working with symmetric functions in Sage. Okay, so first I'll start off by making the Schur symmetric functions and, say, the monomial symmetric functions.
So it just sort of declares the space you're working in, right? It doesn't make anything?
Yeah, it just, so if I type in S, it's a symmetric function algebra over the rational field with these as your basis. So this is sort of the object corresponding to the parent space. Okay. So I can create that, and that's how it shows up in Sage, S of 2, 1. And we can square it. And so all of this stuff for the classical bases are happening within Symmetrica. So because it's in C, it's pretty fast. Yeah, especially if you want to do multiplication in like the Schur basis, it's way faster than say John Steinberg's SF package. So I can do.
Is that because of the interface of Maple, or did you time it compared to?
I just timed it within Maple.
No, within Maple buffer, or within Sage using Maple?
Just within Maple itself. Yeah, it can do.
Composition partitions of like 10 is hard to get. I mean 10 parts.
So, I mean, here's a pretty big partition.
That's good.
Oh.
Output chunk.
So, I guess in the notebook, see there.
You could just
big.
assign instead of printing or something. Yeah.
So it turns out that Sage don't want to send the whole output in the notebook.
So is that going to send it to that file?
Yep.
Yep. So we can click on that.
Nice.
And
One long line.
they're right. It's this huge thing. But I mean, it did it pretty fast.
Yeah.
If I can go up and find.
Probably the time was all spent printing out the answer.
Yeah. Yeah, so I can just assign it to a variable. And
Hmm. That's weird.
Is it done or is it working?
it looks like it's working. There
Yep.
it goes. So I don't know if this calculation is even, well, I gave up after like running something of this size in SF. So you can do arithmetic with symmetric functions very fast within Sage. Okay, so say I have B, which will, let's say 4, 3, 2, 1. Okay. Now, maybe I want to know what is this symmetric function in the monomial basis. So we already have M, which corresponds to the monomial basis. And what do? We just call it with B. And there we go. It performs the conversion between the bases. We can check that M of A squared equals, M of B squared equals shouldn't take that long.
You have to interrupt the
Yeah.
other one.
So if something takes longer than you want, you can interrupt, and that will stop the calculation, which is pretty nice in case when something goes unexpected. So,
Also, hitting the escape key is the same.
oh.
Yeah.
There. So it turns out, I
I
mean,
thought that you were running two things at once. Is that true? Can you run two things at once?
yes.
Well, really what's happening is you can queue up a whole bunch of calculations.
Uh-huh.
So you can hit Shift Enter and have 10 cells queued up, and then it'll do one after the other. Just like with Mathematica or something. But different than Mathematica, you can have several different worksheets at the same time that are completely distinct, running in parallel. Whereas in Mathematica, it's one or the other. You can't have them all at once.
So we could ask what the transition matrix is between the monomial symmetric functions and the Schur symmetric functions for, say, all the partitions of size 3. It turns out the symmetric algebra is graded. Oh wait, you think? Actually, let's do the other way. And if we do so, do these numbers look familiar to anyone? Yeah. Yeah, so the transition matrix between the Schurs and the monomials turn out to be the Koska numbers. And if you say just look at this column, that gives you the number of standard tableau of that shape. So this corresponds to 5, this corresponds to 4, 1, and so on. We can take, what else do we want to do? Oh, plethisms. So B is just this element. And we can take the plethism of B with itself and symmetrical. We'll think for a little bit. Actually, this will probably be pretty big. And there you can perform plethisms. And you can do this in like all of the bases. So for power sum, homogeneous, all of them, you can do plethisms in those bases. You can convert between the two. I can do, say, monomial of 2, 1 plus the Schur of 2, 1, and it will perform the basis to put 1 in the right basis and then perform the addition. So you can mix and match bases like this. And I guess on that note,
So it picked the first element you wrote as to tell it which ring to work in?
Yeah, it's based on like the Sage coercion model. So Sage has a nice model for figuring out how, if you have two things of different types, how you can put them in some structure where like the operation makes sense.
But it's emphatically no, it's not the first one. It's much more sensible than that. Like, do the sum in the other order and see what happens.
Okay.
Yeah, there was a point in time when it was the first one, like 2.5 years ago, but that was a bad design. We have a much more sophisticated design now.
So if you want to force it to be in the monomials, then you just do that, or you could force it to be in there, or I could make SFA power and just put in the power sum. So yeah, on that note, I think that will end and take any questions. Yes.
So were you an undergraduate at UCLA then?
Sorry.
Were you an undergraduate at UCLA? I mean,
I was actually an undergraduate at Harvey Mudd College.
Oh, okay, right.
So
yeah.
it's about 35 miles or so east
Right.
of downtown.
Yeah, I'm a Pomona College, so I know that.
Yeah. Yep.
So when you do, this is a substitution from, I was thinking here, but it keeps going, but then the next step is to make something like the Donald polynomials where you have to stick in different variables and.
Right. So I'll get that and then I get you. So in the next month or so, I'm going to be working on like Hall Littlewood polynomials, McDonald polynomials, and so in that case, we will like the parameters Q and T will be degree 1 elements, and so when you perform the platosome, it'll do like the right thing. But that's not in there yet.
Okay.
Yes.
I assume you can use different rings for coefficients?
Yeah. I think I defined R, so I can make, say, P equals SFA.
And will that use like big numbers if you need to, or
Yeah. Sage is.
smart?
Ooh, no fact.
Oh yeah, sorry.
I don't have it.
I mean,
Yeah, okay.
yeah, it's arbitrary precision. Recently,
What did you do to fix that? Oh, I see. You just went.
Yeah, explanation point just isn't the right notation.
yeah. You can, yeah, it handles arbitrary.
Well, then my other question was, is there any prospective support for quasi-symmetric functions?
Yes.
Close to
Yes, I would like to get to those as well.
You too could be part of this.
Yeah,
Yes.
I mean, it's all a matter of like time.
Priorities, yeah.
Yeah, but if you have an interest in working with quasi-symmetric functions in Sage, then I would be happy to get quasi-symmetric functions in Sage.
All the different bases, yeah, it seems to just follow the pattern here from symmetric functions.
Because right now I have my own code base that I'm just of my own for working with that and stuff.
Yeah, and I'm sure there's probably other people interested in them. I know someone just asked about non-commutative symmetric functions, and so yeah, there's lots of work in this area that would be good to have in Sage and that people would be interested in.
Great, thanks again.
Oh, thank you very much.